Hello and welcome to the module 4.2. And in this module, what we are going to cover is the probability essentials. We'll try to understand the basics, we'll try to understand the concepts, fundamentals, those are associated with the probabilities. How we can identify the uncertainty, how we can identify the randomness in the data. And those fundamental concepts would be good enough for you to know and apply in any kind of analytics that you are doing. So, are you guys ready? Let's move to the probability essentials. We'll learn this again in the same way we have learned the descriptive statistics. So there are some core concepts that we'll learn, like what is random rules, then the conditional probability, then Bayes rules, then common and discrete, and the continuous distributions. So these are the all core concepts. If you learn these core concepts, then I think the probability that you need for your analytics is more than enough. You don't need to get a mastery, you don't need to get be a professor of the probability essentials. You just need to learn basic and simple rules, core concepts that I just highlighted here. So learning objective is again the probability essential. First, like, we'll understand how to define the events, compute the independence, how to get the conditional probabilities. Then we'll use the Bayes rules to recognize the key distributions and key parameters. And then at last, we'll go for the computing simple probabilities using the example data. We'll load some kind of examples, we'll give some numbers and try to compute the probabilities so that you learn the basics behind it. Then there are random variables and notions. There are multiple things here. For the random variables, you have a distribution of the parameters in total, and that we have learned in the previous, also in the descriptive statistics. Then you have PMF, discrete and continuous variables. For discrete and continuous, you get these kind of uh, uh, variables to store. And then for the CDFs, it gives you the probability values which are lesser for the smaller than the higher values. And at last is the expected value, which is a long term mean. So you don't need to learn the formulas, you just need to learn these key variables which we are talking about. What is a random variable, what are the notions, how you define from the total distributions, from the discrete and continuous distributions, and from the expected values which you compute from all the datasets as a long run mean. And if you remember, we computed the mean by just taking the cumulative average and dividing by the total number of instances we have. Okay. Then it comes to the rule of probability, and rule of probability can be divided in four components, four fundamental principle. First fundamental principle is probability is always between 0 to 1. So this is like you can identify anything, like if you are flipping a coin, and what are the chances of getting heads versus tails. So this, the probability range will range always between 0 to 1. If the chances of coming head is zero point 0.4, then the chances of coming tail will be zero point 0.6. So always this will lie between 0 to 1. Now you can flip a dice also. If you will flip a dice, what are the chances of getting 5, getting 4? What are the chances of getting 8? There will be no chances, because in the dice there is no 8 number. So those kind of things you can get. The number have, the variables that you have, if you are using those, trying to find out the probability, it will always lie between 0 to 1, and that is the first fundamental principle. Second fundamental principle is the probability of complement, and that is very very important to learn. So let's say A is a event. If A is a event, then what are the chances of happening that particular event? Then this A square C will be the completely opposite to that event. And how you do that? Chances of rain, that there will be a rain today. If the chances of getting rain today is 0.3%, then their chances of not having rain today will be 0.7%. So this is the complete probability of complement. There is one event, you are predicting the probability of that event, and then the opposite will happen to the another event that you are not defining. Simple. The third, very important, is the addition rule in the probability. Addition rule is very very important. Now, if I will ask randomly, what are the chances among all the people we are putting together? What are the chances that people will like coffee? So you will say, let's say, for example, there are 60% of the chances, so probability is zero point 0.6, that people will like coffee, or people will love coffee, drinking coffee. Then there will be chances of people will love drinking tea, let's say. and the chances of people love tea or like tea is 0.5%. So 0.6 plus zero point 0.5 more than 1. But that's not the case. Whenever you are using the rule of addition, you need to find out the common thing also. You need to subtract the common. There will be people who are liking both coffee and tea, so you need to subtract those individuals from the individual probabilities. So you will get a probability of people who are liking coffee is zero point 0.6, probability of people who are liking tea is zero point 0.5, so the probability so far is 1.1. Then you need to subtract the people who are liking both coffee and tea, and that's, let's say, is 0.3%. So you will get the point probability by addition rule. That means 80% of the individuals from any given sample population will like either tea or coffee. So this is the addition rule, and you need to understand it. The last fundamental principle is the independent principle, in which both probabilities are completely independent from each other. How? So, for instance, if you are flipping two dice at the same time, what are the chances of getting 5 in one dice and chances to get 4 in another dice? These are the completely independent probabilities, because here are the complete random chances, here are complete random chances. So, when you compute the independence, then you need to multiply those probability scores to get a cumulative probability of two dices flipping together. And this is an example of the independence, where two events are completely independent from each other. After this, we learn about the conditional probability, and we learn about this. So in this very simple and very short, probability of event A occurring given that the event B has occurred. So for this, the probability of A by B. What is the probability of occurring A or coming A when event B is already occurred? So for this, you will compute the probability of A by B and then divided by the probability of the event B which is already occurred. So by this, you can get the conditional probability, not independently for one, but A is dependent on the B. So that's how you calculate the conditional probability. Now you go Bayes rule, and in this, if you are getting the probability of A and B, you can go for from the basic form, and in this, update the prior belief. You have some kind of prior belief with the evidence of B to get the probability of PA by B. So now in this, you have some prior data or prior belief, anything. Like if there will be 5, then there are high chances, so there is certain kind of probability associated that in another dice you will get 4. So this is the prior belief that you use here. So for this prior belief, you use the prior belief as a probability of A, which is expected probability. Probability B you already know, and then you use this probability of B by A, in which the B is the event that already occurred, A is the prior probability that you are getting, and by doing this, you can get the Bayes rule, the probability of A by B. The only difference between conditional probability and the Bayes rule is, in conditional probability, you are not using the prior beliefs or the prior experience with the data or prior knowledge with the data in form of the probability for the new event. Now the Bayes rule in the expanded form, if you will expand this Bayes rule, then it is useful when PB is unknown specifically. So these kind of rules you apply when you already don't know what is occurring. The event, the B which is occurred already, you don't know the probability of that as well. So you can do the expanded formula. Again, there is no need to or like remember these formulas, but you understand the conditional probability, what limitations and advantages it will provide. The Bayes rule, it will definitely add some prior information, so it can provide a little bit more meaningful information from the data that has been already tested and validated. And then in the Bayes expanded, you can add a little bit more information here. These kind of conditional probability Bayes expanded rule can be used in the medical diagnosis, spam filtering, and updated the scientific hypothesis from the new data. Now you go for the discrete distribution, the key probability distribution for count and the binary outcome. So these are three mainly. So you will go for the Bernoulli, you will go for the binomial, and then Poisson. So Bernoulli is a model in which there is a single binary outcome 0 by 1 with the probability of success p. So you have a mean and you have a variance. You have a probability of success, you get the variance by that probability of success multiplied by 1 minus probability of this, and you will get the mean. These two are very very important for Bernoulli type of model distributions. Then you go for the binomial distribution. So in this, you consider the number of success in the independent Bernoulli trials. So if you do the independent Bernoulli trial, you have the number of successes also. So you add those number of successes to compute the variance. You add those successes into the mean. So that's a binomial in which you add number of successes along with the normal formula that you Bernoulli. So from the Bernoulli, you get the trials, you get the number of successes, and add in the formula, then you will get the binomial. Then the Poisson. So in Poisson model, count for the event in fixed time and space interval. So you have already counted some kind of events in the fixed amount of time and different type of a space interval. You will get some kind of mean and variance. So that is a Poisson distribution. So these are the mainly three kind of distributions. What kind of distribution you are applying on the data, and then you will learn. So try all three when you are checking the distribution of any numerical variable. Try Bernoulli, try binomial, and Poisson distribution, and you will see the differences. Okay, these parameters, of course, control the mean, variance, and the shape of the distribution. Then you go for the continuous distribution, which is probability distribution with infinite possible values. In continuous, you will get a lot of values. So it can be uniform, like flat distribution with equal probability across the ranges. If you're getting the distribution a horizontal line, so you can't compute the probability which is changing. It is a continuous probability, flat distribution, and equal probability for all the data points. Then there is a normal distribution, in which, like, we generally discuss the well-shaped curve, the symmetric around the mean is exactly at the center, left hand side, right hand side is the lower values. This is a completely well-shaped curve. This is considered as a normal distribution. Then you have an exponential, in which model time between the independent events. There can be multiple independent events, and you can get this skewed type of curve. Then log normal and binomial, the right skewed distribution for phenomena like income, asset prices, and everything. So in which it's like it can be left skewed or right skewed, but in this specifically phenomena, we talk about the income and asset prices which keep on increasing. So in which you will get the data which is right skewed. Okay, anything that you will take which is like depreciating events, like if you're buying something, their price will be getting down, like the car or anything, any kind of assets, that can be the left kind of a skewed distribution. Those things you can learn. So normal distribution, again, we have learned the empirical rule of the normal distribution, which is like the center is the mean, and then you are getting the data something like this. So you are getting the empirical rule of 68, 95, and 99. In this, you cover the three quartiles. One deviation, Z score is always normalized from the x minus mean divided by standard distribution. So many statistical the central theorem, in which you get the perfect distribution of the data, starting from the lower the number, center is the very high, and peak you will get at the mean point where you are getting the data mean, and then the right you will follow same as the left. This is the complete normal distribution. After getting the distribution, you go different kind of tests like t, chi-square, and F distribution. So t distribution is used for the mean with unknowns. So heavier tails than the normal approach the normal distribution and normal degree of freedom. This is very important to learn. Then you go for the chi-square, where you use the variance and contingency tables, always positive and right skewed for the distribution. At last, we learn about the F distribution, used variance like ratios such as ANOVA, MANOVA. You have learned a lot of things, ANOVA type of things you can do here for F distribution. The ratio of two chi-square distribution. This is very important foundation for comparing different groups. And then all arise from the sample variability, critical for the hypothesis testing. So you need to decide whether you want to go for the chi or F type of distribution or T type of distribution. It depends on the how the data behave, how the distribution is, whether those the groups you are comparing are in the paired format or unpaired format. So those kind of things before going for the any kind of distribution to try. Okay, now, if you can take the examples of binomial probability. So identify the variable that is first. Let's say number of trials are 10. Probability of success. If you're looking for the probability should be greater than or equal to 3, then recall the binomial formula. You can use the binomial formula and you can get how much success you will get from this data set for a specific number of success in the k binomial distribution. This kind of formula can be used. Then calculate the direct approach. Like to find px greater than 3, we would need to sum all of the individual probability for all the data point trials that you have done from 0 to 10. Then if you use The complement rule, more efficient rule. In the complement rule, you learn, previously we discussed about it. There is always the probability of one minus, like there is an event which is going to happen, and then there is a opposite of this event. What will be the opposite of the event is exactly the probability that you are getting here. One minus that probability will be the opposite of that. And this you will do for all 10 instances that you have, all 10 trials that you have. You will do the probability 1 minus the probability of one event, 1 minus the probability of second event, 1 minus probability of the third event, and that you will keep on doing. Okay. And that's how you get the complement rule, and you get the more efficient information about the probability. Now, example of normal probability, you need to define the problem first. So define the IQ scores, follow the normal distribution, and get the information from there. Then standardize to the Z scores, get the Z scores from the normal distribution. Once you get the Z scores, then you calculate the standard normal format for CDF. And once you get the standard probability approximation, interpret the results. And these IQs can be anything. It depends. If you are making the box plots, you can go for the 25% quartile, you can go for the 75% of the quartile. You can get the IQ scores. From those IQ scores, you can compute the standard deviation, and from those standard deviation IQ scores, you can get the outliers, and then decide what to do with them. Like, you want to remove them, you want to impute them. So far we are learning all the concepts, all the basic things. We are just revising for the probability, and what you need to learn, what you need to know here. We are not doing any hands-on experience for all the things we are learning. We'll do quickly at the end of this class. Key points to remember in the probability ranges from 0 to 1, which is a first fundamental principle that we are discussing here. The conditional probability is very, very important. When probability of B affect the probability of A, choosing the right distribution, the data characteristic, is extremely important. You can check some of the pitfalls here, like treating continuous variable as a outcome of the zero. It's actually zero when it is actually zero. Confused events, when there are two independent events but those are actually confusing. Mutually exclusive events, you can ignore that. Then ignore the meaning of distribution parameters like shape, location, and skills. Those things you can ignore here. Now, you can quickly check if two events A and B are completely independent, which of these statements are true, whether the answer is this, is it true or not. You can check this. You can check these kind of questions for each and every principle we have learned. Just take a simple data, compute the probability for all four fundamental principle, and you are good to go. This is more than enough for you to know in the probability essentials. Now we'll move part, which is sampling and intervals. So see you in the third part.